Let's first define the column space of a matrix. Let A be an m by n matrix. Then the column space of A, denoted by column A, is the subspace of Rm spanned by the columns of A. So we let the columns of A be the vectors C1, C2, all the way to Cn, which means that our A matrix can then be expressed as C1, C2, Cn. Then the column space of A can be written as span of C1, C2, all the way to Cn, which means that it is the set of all linear combinations of the column vectors C1, C2 to Cn. Now let's try to investigate the concept of a column space further. We consider the linear system Ax equal to B. Now to be concrete, we let A be a 2 by 3 matrix. Then the product Ax can be seen as the image of x under the linear transformation Ta, where in this case Ta maps the vector x in R3 space to the output Ax in R2 space, where our x here is in R3 space, output Ax is in R2 space, and our B is also in R2 space. Now on the figure transformation diagram here, we have our R3 space, and then we have our R2 space. A certain element x here is being mapped to its image. We call this Tax. Now the column space of the matrix A is defined as all linear combinations of the columns of A. So this is actually equal to Ax using the column view for all x in R3 space, the input space. So each vector x in the R3 space is being mapped to its image Tax in R2 space. The set of all images constitute what we call the range of the transformation, and in this case it is called the column space of A. In fact, the column space of A is just a subspace of the R2 space. As you can see here, it may not necessarily span the entire R2 space. Typically, it is a subspace of the R2 space. Now, let's consider a certain given vector B. If this vector B lies outside of the column space of A, which means maybe it lies here, so this is our B vector, then no matter what set of x values we choose, no linear combination of the columns of A can reproduce B. So for this case, we call it case 1. If B lies outside of the column space of A, that is, B is not in the column space of A, then this implies that Ax equal to B has no solution. For the other case, case 2, if our vector b lies within the column space of A, so on this figure, it will look something like this. Your vector b, case 2, lies within the column space of A. Then we do have at least one linear combination of the columns of A that can reproduce B. So in this case, B is in column space of A, and this implies AX equal to B is consistent. So I hope this explanation has given you a deeper understanding of the column space of A with respect to the solution to the linear system AX equal to B. So we arrive at this theorem that says that a linear system AX equals B is consistent if and only if B is in the column space of A. Conversely, the linear system is inconsistent if and only if B does not lie within the column space of A. Now let's take a look at this question. Determine whether B is in the column space of A, where A is this 2 by 3 matrix and B is a 2 by 1 vector. So for part A, remember that B is in the column space of A if and only if AX equal to B is consistent. So in this case, we just have to find out whether or not the linear system is consistent by looking at the augmented matrix. Which is, in this case, equal to 1, 0, minus 1, 3 for the first row, 1, 1, 1, 2 for the second row, and this can be reduced to row 2 becomes row 2 minus row 1. So that will give you where you can immediately identify the pivots. One's a pivot, this is another pivot. So as you can see, the system is consistent because the augmented column has no pivot. So therefore, we say system is consistent. This implies that B lies within the column space of A, and that is the answer for part A. For part B, the augmented matrix is equal to 1, 0, 1, 1, 2, minus 1, minus 3, 1, minus 4, augmented by this column 1, 1, 0. And we can once again perform our row reductions. Row 3 becomes row 3 minus row 1. That will give us 1, 1, minus 3, 1, 0, 2, 1, 1, 0, minus 2, minus 1, minus 1. Right, so here immediately you can identify that we have two pivots, this number here and this number here. So the next step is to get rid of the minus 2 below the second pivot, and to that end we apply another row operation. Row 3 becomes row 3 plus row 2. So that will give us 1, 1, minus 3, 1, 0, 2, 1, 1, 0, 0, 0, 0. So once again, we have 2 pivots, and the augmented column has no pivot, therefore the system is consistent, and our vector B is in the column space of A. So that's the solution for part B. Now, an important point to note is that elementary row operations may change the column space of a matrix. So to demonstrate why this is the case, let's consider a certain matrix A, which is a 2 by 2 matrix, 1, 3, 2, 6. Let's try to reduce it to RREF, the reduced row echelon form. R2 becomes R2 minus 2 times of R1. And we will then have 1, 3, 0, 0. And let's call this matrix R. Now, the column space of A is just T, 1, 2, such that T is a real number. Okay, because 3, 6 is a scalar multiple of the column vector 1, 2. Therefore, the column space of A can be written as a scalar multiplied by the vector 1, 2. On the other hand, the column space of R can be written as the parameter S multiplied by the column vector 1, 0, such that S is a real number. This is because the other column vector 3, 0 is a scalar multiple of 1, 0. Therefore, the column space of R consists of all vectors of this form, where S is a real number. So we can clearly see that the column space of A is not the column space of R. That is, they are different spaces, and therefore elementary row operations may change the column space of a matrix. Now, for a simple case of a 2 by 2 matrix A, we can easily find the basis of the column space of A by inspection alone. What about 3 by 3 or in general n by n matrix? Therefore, we need to find a systematic procedure to compute the column space of a certain general n by n matrix. And this is our task in the next slide. Next, we will learn how we can find a basis for the column space of a matrix using this theorem. Suppose we have a matrix A that has been reduced to its row echelon form R. Now, there are two important observations. First, the pivot columns of R form a basis for the column space of R. Why is this the case? We note that the pivot columns are linearly independent, as can be deduced from the positions of the pivots. For example, no two pivot columns have pivots in the same row. Also, the pivot columns span the column space of the matrix, since all other columns can be written as a linear combination of the pivot columns. Therefore, the pivot columns form a basis for the column space of the matrix. For point number 2, a given set of vectors of A forms a basis for column space of A if and only if the corresponding columns vectors of R form the basis for the column space of R. To understand why this is true, first we note that elementary row operations do not change the solution set of a linear system AX equal to 0. Right, this is obvious, otherwise there's no point in performing elementary row operations on a linear system. So this would mean that the homogeneous linear system AX equal to 0 and Rx equal to 0 have the same solution set. Alright, next we let A1, A2 all the way to AN be the columns of matrix A, and also R1, R2 all the way to Rn be the columns of R. Now, if we have C1A1 plus C2A2 plus all the way to Cn An equal to 0 for some C1 all the way to Cn, which are real numbers, and this would imply that the same coefficients also satisfy the system Rx equal to 0, meaning that C1 R1 plus C2 R2 plus all the way to Cn Rn is also equal to the 0 vector for the same C1 all the way to Cn, which are real numbers. Therefore, we conclude that the column vectors of A and the column vectors of R have the same, what we call, dependency relations. Right, they have the same dependency relations. Now what this means is that if a certain subset of the column vectors of R are linearly independent, then the corresponding subset of columns vectors of A are also linearly independent. Therefore, point number 2 states that a given set of column vectors of A forms a basis for the column space of A if and only if the corresponding column vectors of R form a basis for the column space of R. Now we will make use of these 2 points in the following examples, where we will be asked to find a basis for the column space of a certain matrix A. In this question, we are asked to find a basis for the column space of the matrix R, which is already in row echelon form. So our task is very simple. The first step is just to locate the pivots, which are this 1, 1 and 1, which means that the first column, the second column and the fourth column are pivot columns. Therefore, a basis for R is given by the first column vector 1 0 0 0, the second column vector -2 1 0 0, and the fourth column vector 0 0 1 0. This is a consequence of point number 1, which was discussed earlier. The pivot columns of R form a basis for the column space of R. In this example, we are supposed to find a basis for the column space of matrix A. For part A, we have a 2 by 3 matrix. A is given by 1 0 -1 1, 1, 1. And recall that to find the basis for a certain matrix, we have to compute the row echelon form, identify the pivot columns, and then the corresponding columns from the original matrix A will be the basis for the column space of A. So we perform the row operation R2 minus R1. That is to get rid of this number 1 below the first pivot. So we have 1, 0, minus 1, 0, 1, 2. And we can immediately identify our pivots to be 1 here and 1 here. Let's call this R. So this would imply that our pivot columns are columns 1 and 2. Therefore, a basis for column space of A is equal to, according to what we have just learned, the given set of column vectors of A form a basis for the column space of A, if and only if the corresponding column vectors of R form a basis for the column space of R. So now we know that these two column vectors form a basis for the column space of R, and these are the first and the second columns. Therefore, the corresponding columns of A are 1, 1 and 0, 1. And these will form a basis for the column space of A. So we have 1, 1 and 0, 1. And that's our answer for part A. For part B, our matrix is slightly bigger. We have a 3 by 3 matrix. A equals 1, 1, minus 3, 0, 2, 1, 1, minus 1, 4. And then once again, we perform the row operation. Row 3 minus row 1. In this case, we get rid of this number here below the first pivot. So we end up with 1, 1, minus 3, 0, 2, 1, 0, minus 2, 7. And we can immediately identify our second pivot, which is this number here. And we are supposed to get rid of the number minus 2 below the pivot. And we perform the row operation, row 3 plus row 2, to obtain 1, 1, minus 3, 0, 2, 1, 0, 0, 8. Our pivots are 1 here and 2 here. Therefore, the pivot columns are columns 1 and 2. And therefore, a basis for the column space of A would be from the corresponding columns of the matrix A, we have 1, 0, 1 and 1, 2, minus 1. And that's our solution for part B. Our last question for this lesson is to find a basis for the space spanned by the given vectors. We are given 5 vectors here. So, how do we find the space spanned by a given set of vectors? We simply make use of what we already know to compute the column space of a certain matrix. Okay, let's see how we can do this. First, we let the vectors be denoted by V1, V2, all the way to V5. There are 5 vectors here. And then we let the matrix A be formed from the 5 vectors and put them to the columns of the matrix. In other words, we form a matrix A whose columns are the vectors V1 to V5. So our matrix A looks like this. This is a 4 by 5 matrix. Now this can be row reduced to the RREF, the reduced row echelon form, to this matrix. And we can immediately identify the pivot positions to be this, and this. These are the leading entries of the first 3 rows. Now, this is the reduced row echelon form, but typically we do not need to compute the reduced row echelon form. The row echelon form is enough for our purpose. So in this case, straight away you can see that the pivot columns are the first column, the second column, and the fourth column. So these are the pivot columns. Therefore, a basis for the column space of A would be the first column of A, which is 1, 0, minus 3, 2. The second column of A, which is 0, 1, 2, minus 3. And the fourth column of A, which is 1, minus 3, minus 8, and 7. Now, this basis for the column space of A is also the basis for the given set of vectors. And that is our final answer.